So example 2. So a survey was given as to how long customers at Lucky, this restaurant, claim to wait in the checkout line until their turn. Determine if the data are approximately normally distributed. And so the time below here is in minutes. So here's the data. So let's assess the normality here. I've done 4 different types of displays to start us off. Histogram, a dot plot, a box plot, and a stem and leaf plot. All of these lend credence to the fact that these wait times did come from a population that was normally distributed. So on the TI-84, you put the data into L1, and when you turn on your stat plot, the type is the 6th one over here. This is the normal probability plot, and just make sure that we have our data in L1, so make sure you have the data list as L1, and we're going to do this against the x-axis, and it doesn't really matter what mark you choose. And again, it's roughly linear, so it's reasonable to believe that data did follow a normal distribution. I also ran a QQ plot in StatCrunch, very similar to the normal probability plot again, interpreted exactly the same way. So a little note here, not all software computes these values in the same way. The overall pattern, though, is evaluated exactly the same. We're looking for systematic departures from normality that would disqualify the data set as coming from a normally distributed population. So I wanted to show you here one value, how this is computed. So what we do is we look at that value here. We have one value here. It's at negative 1.75, and this one happens to be positive 1.75. This is the second smallest wait time out of 50. So it corresponds to a percentile of about 0.04, 2 or 50. If we do the inverse norm of 0.04 on the TI, we get a z-score of negative 1.75. That's where this negative 1.75 comes from. And if we look up to our red line, this should correspond to 1.75 on the data set. In fact, on this one, it's practically right on the money. Not all of them are like that. And StatCrunch does this for each value it plots. So they're rarely going to be exactly on the line, but we're looking for a pattern, a trend for the data like we normally do in statistics. So what would a QQ plot or a probability plot look for a skewed distribution? So it would not be linear. So a normal probability plot would also show a nonlinear pattern. As we will see here, this QQ plot does not lie along a straight line. So this confirms that distribution is indeed. We can look at our histogram here and we can tell this is clearly a skewed distribution and how it corresponds to the QQ plot. Similarly with the box plot, we can tell this is going to be skewed. We see this really long whisker here. So this indicates a skewed distribution. Another one, example 3, this is strictly using the TI. We have a left skewed histogram here at the top, and its corresponding box plot indicating non-normal, and then more confirmation is the probability plot here in the bottom. This does not lie along a straight line. There's some definite curvature to the plot. So in some sense, determining normality can be pretty subjective, almost akin to reading tea leaves. So rubrics for grading the free response questions regarding normality will often give either answer. It is normal versus it is not normal. It all depends on justification. So the graders for, if you're taking the AP exam, have they can give full credit for either the student says it is not normal, and it gives full credit for the student says it is normal. It depends on their justification. So I recommend creating as many displays as needed to make your case for or against normality. So this includes histograms, dot plots, box plots, stem and leaf plots, probability plots. Much of this sort of depends on the context and the size of the data set.